Hello there, and welcome to the Sleepless Scientists, your quiet corner of the cosmos where curiosity meets calm and science gently lulls you to sleep. Before we begin our journey tonight, I'd love to know, where in the world are you listening from, and what time is it right now? Feel free to share in the comments below. I'm always amazed by how many of us are drifting together from different corners of the globe. And if you enjoy tonight's voyage, consider giving this video a gentle like and perhaps subscribing to the channel so you don't miss our next dreamy exploration. It really does help more sleepy minds find their way here. Now, tonight's story is a beautiful one. How life, in all its complexity, may have first emerged from lifelessness. The origins of life on Earth. I do hope it's not so intriguing that it keeps you awake. But if it does, well, at least you'll carry a bit more wonder about our own beginnings into tomorrow. So settle in. Let your shoulders drop and your breathing soften. Get cozy under the blankets. You're about to drift back through billions of years to the very dawn of life on our planet and even beyond. No rush, the story will unfold at its own gentle pace and the molecules will wait for us. Let's begin. Over 4.5 billion years ago, our Earth was a newborn world, a hot, glowing sphere of molten rock drifting in the darkness. But even before that, the seeds of life were being prepared elsewhere. In ancient stars that lived and died long before our sun, the elements of life were forged: carbon, oxygen, nitrogen, and more. Those stardust elements swirled in a vast cloud, gathering under gravity's gentle pull. And in time, that cloud became our sun and its planets. Earth was born from this cosmic dust and fire, carrying in it the ashes of stars, the ingredients for oceans, and for life itself. Perhaps one of those atoms was a tiny grain of carbon forged in such a supernova. For ages, it drifted through the galaxy, cold and alone, until gravity drew it into that forming cloud of our solar system. It became part of the young Earth, trapped in a piece of rock. When the rains came, that rock crumbled and the carbon atom washed into the primitive ocean. There, it joined with other elements to form one of the first organic molecules, maybe an amino acid floating in the warm sea. In time, that molecule might have been woven into a primitive strand of RNA, part of the very first stirrings of life. And eons later, that same carbon could even find itself inside you, part of a cell in your body as you listen now. It's a humbling thought. The atoms of our bodies have journeyed through stars and deep time to be here, tying us to the cosmos and to the origin of life itself. In its infancy, Earth was violent and wild. Meteors and asteroids rained down endlessly. Every night, countless shooting stars streaked across the sky, a relentless fireworks show with no audience. Each fiery trail briefly illuminated the clouds, then faded as more and more space rocks found their new home on Earth, delivering heat and materials. Each impact shook the ground, and the heat kept the surface molten. There was no water yet, only steam hissing from the cooling rock. Volcanoes dotted the landscape, endlessly erupting, painting the sky with thick clouds of gas and ash. It was a world in flux, a place of constant dawn and dusk under a reddish, hazy sky. Not long after Earth formed, it endured a titanic collision. A wandering planet, perhaps the size of Mars, grazed our fledgling world. In that colossal impact, Earth nearly melted all over again. A spray of molten rock shot out into space, forming a glowing ring around the Earth. For a while, our planet may have looked a bit like Saturn, with brilliant arcs encircling it. But gradually, that ring of debris clumped together and a new companion was born: the Moon. In those days, the Moon hung much closer to Earth than it does now, a giant glowing orb in the sky. Night after night, it loomed huge and bright, its face still hot and molten, tinting the nights with an eerie orange glow. Its gravity tugged at the young Earth, stirring the magma and later the tides of the oceans to come. For millions of years, chaos reigned. To an outside observer, it might have seemed endless, but for the young Earth, this was just the fever of youth, a turbulent beginning that would eventually quiet down with time. But gradually, things began to calm. The rain started, at first, scalding hot rainfall that sizzled against the cooling rocks, then more and more as the Earth's surface cooled. Water vapor that had been trapped in the thick air now condensed into liquid. It fell in torrential sheets for centuries, pooling in low basins. Comets and icy asteroids brought more water, delivering it from the far reaches of space. With that water, they likely sprinkled the Earth with organic molecules formed in the cold of the cosmic dark. Indeed, billions of years later, humans would find meteorites containing amino acids, the very building blocks of proteins, showing that the heavens had been seeding Earth with life's ingredients all along. Little by little, shallow seas and great oceans spread across the scarred surface. Imagine standing at a safe distance and watching warm rain fall from copper-colored clouds. The droplets gather in craters and crevices, slowly filling them like bathtubs. Over years and centuries, those puddles grow into vast lakes, and lakes merge into the first true seas. Eventually, a primordial ocean stretches out as far as the eye can see, glimmering under the dim, young sun. The Earth, at last, had water, the gentle cradle that life so desperately needs. From a furnace, the planet had transformed into a realm of water, rock, and sky. Still, it was nothing like the Earth we know now. Barren rock jutted above the primordial seas, forming the first islands and shores. There was no soil yet, no grass or microbes to soften the stones, only naked crags and cliffs under an alien sky. The landscapes were stark and sterile, beautiful in their simplicity. Each coastline was a place where waves met rock in solitude, awaiting the touch of life that had not yet come. The air was thick with carbon dioxide and nitrogen, with traces of methane and ammonia. There was no oxygen to breathe, no ozone layer to filter the harsh sunlight. The sun's rays beat down unfiltered when the clouds parted, and lightning still flickered in the humid air. Yet, in the midst of this seemingly inhospitable world, a quiet miracle was brewing. The stage was set for the first whispers of life. At first, life itself did not yet exist, but the waters and skies were busy preparing the ingredients. Think of the young ocean as a vast, simmering cauldron, a primordial soup rich with potential. Volcanoes were still bubbling under the sea, releasing minerals and heat. Lightning forked across the sky in brilliant flashes again and again, striking the water and land. Each lightning bolt was like a stirring spoon in this planetary pot, energizing reactions among the gases in the atmosphere and the compounds in the water. In those electric moments, something remarkable happened. Simple molecules transformed into more complex ones. The nitrogen, carbon, and hydrogen swirling in the air and ocean recombined into new forms. Tiny organic molecules began to appear, among them amino acids, the building blocks of proteins, and other bits of chemistry that life would one day use. These newfound molecules rained down with the droplets and collected in warm, shallow pools along coastlines. With each day's rain and each burst of lightning, the pools grew a little richer, a little more complex. The water might have even taken on a faint color or scent from these organics, a subtle golden or brownish tint as the broth of life thickened. Of course, this was no soup fit for any human kitchen. It would have smelled of sulfur and chemicals, utterly toxic to us. But for those budding molecules, it was a rich and welcoming broth, exactly what was needed. At the same time, the rhythms of the young Earth itself were at work. The moon, so much closer back then, pulled on the oceans with tremendous force. Tides rose and fell dramatically, perhaps flooding vast stretches of shoreline, and then retreating over and over. Imagine the sea rushing in, mixing everything together, then pulling back and leaving behind countless shallow pools along the beaches. These pools would slowly evaporate under the sun, their waters growing dense with dissolved molecules, only to be refilled when the next tide swept in. Back then, Earth spun faster on its axis, so days and nights were shorter than today. The sun rose and set rapidly, perhaps completing a full day-night cycle in what would now be just 12 or 16 hours. This brisk pace meant the warming and cooling, the tides rising and falling, all happened a bit more frequently, like a planet with a quick heartbeat. This daily pulse of the ocean was another gentle stirring, a slow heartbeat for the primordial soup. By day, the sun warmed those puddles and ponds, sometimes drying them out under its rays. As water evaporated in the heat, the chemicals left behind became more concentrated. Perhaps crystals formed along the edges of rocks as the liquid receded. And when the rains came again or the tide rolled in, the pools refilled, mixing everything together once more. Wet and dry, concentrate and dilute, the cycle repeated over countless days and nights. These rhythms of nature, the sun and the rain and the tide, might have helped simple molecules link into longer chains. One can imagine around the edges of a quiet tidal pool, thin films of organic residue, perhaps sticky and tar-like, coating rocks as the evening cools. Each film was a random experiment in chemistry, waiting for something more to happen. Years later, in modern times, scientists recreated a tiny version of this ancient scenario in their laboratories. In a glass flask, filled with gases like the early Earth's atmosphere and a pool of water, they sent sparks of electricity to mimic lightning. The result was astonishing. The clear water turned reddish-brown and was soon filled with amino acids and other organic compounds. This showed that nature, even without life, could produce many of life's ingredients spontaneously. On the early Earth, no flask or scientist was needed. It happened out in the open, under the broad sky, in countless puddles and oceans all at once. The planet itself was the laboratory, and time was the experimenter, patiently stirring the pot for millions of years. This idea that life's building blocks assembled in a warm primordial soup paints a picture of life emerging gently from chemistry, like a dawn unfolding after a long night. In these sunlit shallows and quiet ponds, with the sky flickering from distant storms above, the pieces were slowly falling into place. And between the flashes of lightning and the showers of rain, there were calm periods too. Imagine an early dawn on that ancient Earth, the air warm and still, a thin mist clinging to quiet pools. No animals or insects chirp, only the soft sigh of wind over water and the distant rumble of a far-off volcano. In those tranquil moments, the chemical broth sat under the sky, ripe with potential, as the gentle morning light played over its surface. The world was waiting, holding its breath for that first spark of something living. But where and how would those pieces finally come together into something we could call alive? To explore another possibility for life's cradle, we must dive deep beneath the ancient waves. Far below the surface, where sunlight fades to nothing and eternal night reigns, the ocean floor was alive with its own kind of activity. Here, at the cracks in Earth's crust, hot fluids seeped out from below, mixing with the cold seawater above. Mineral-rich water, warmed by the heat of the planet's interior, gushed or trickled up through vents on the seafloor. As it did, it carried dissolved chemicals that had been brewing in Earth's rocky heart. When this warm, alkaline water met the colder, more acidic ocean water, something magical occurred. Minerals began to solidify, falling out of the water and building structures. Over years and centuries, these structures grew into towers and chimneys of stone, ornate and otherworldly, like underwater castles rising from the dark. Some were delicate and white, others dark and smoky. They emitted a faint warmth in the surrounding water, an oasis of heat in a cold, black realm. This was a landscape of darkness lit not by sunlight, but by the gentle heat of the earth itself. Down here in these deep-sea gardens of stone, the conditions were stable and sheltered. The chaos of the surface, the meteors, the UV radiation, the storms, did not reach this far. Instead, there was the steady bubbling of warm water, the quiet crackle of mineral formation, and a rich soup of chemicals dissolving into the surrounding sea. Within the walls of those rocky chimneys were countless tiny pores and chambers, like a natural honeycomb or sponge. In each little pocket, warm fluids could linger a bit longer before drifting out, creating microcosms of concentrated chemistry. One can imagine these pores as the earliest laboratories of life, cozy little rooms where molecules bumped into each other again and again, perhaps forming bonds in the privacy of those stone-walled spaces. Picture the water percolating through these microscopic chambers. A warm current enters, carrying hydrogen and minerals from the Earth's crust, while a cooler current brings in carbon dioxide from the ocean. They meet within the tiny room of rock, and a reaction sparks, perhaps forming a new compound, a precursor to life. The little chamber might hold onto this new molecule just long enough for another reaction to modify it further. Eventually, a gentle burp of water carries the molecule out into the sea, and the chamber is ready to create more. In this way, the vent's porous labyrinth could serve as a natural workshop, assembling complex chemistry bit by bit, like an assembly line hidden in stone. Unlike the sunlit pools above, here the energy-driving chemistry came from the Earth itself. The warm fluids carried hydrogen, sulfur, and other reactive minerals. Chemical reactions sparked wherever the two waters, one hot and mineral-rich, one cold and brimming with carbon dioxide, mingled along those chimney walls. These vents created natural energy gradients, a bit like the battery of a cell. In fact, every living cell today relies on such gradients, differences in ion concentrations across membranes, to generate energy. And here were similar gradients, ready and waiting in the deep ocean, provided freely by geology. It's as if the Earth was lending a helping hand, offering a gentle power source for nascent life. Some scientists believe that in these very vents, life may have quietly begun. Perhaps within a tiny rocky pore, a set of molecules managed to assemble into something that could grow or replicate. The rocks could have acted like the first cell walls, keeping the ingredients together until they learned to build membranes of their own. And indeed, even today, these hydrothermal vents teem with life. Strange creatures like tube worms, pale crabs, and heat-loving microbes thrive in the darkness, drawing energy from the Earth's warmth, just as the first life might have. It's a heartwarming thought that life could find a foothold even in utter darkness, nourished by the planet's inner fire. In the hush of the deep sea, amid the slow-rising plumes of mineral-laden water, one can almost sense how patient and persistent nature can be. Millions of years could pass in that dark world with chemistry slowly ticking onward, setting the stage for a moment of emergence. Perhaps down here, as much as in the sunny shallows, the pieces of the puzzle were assembling different pieces under different conditions, but aimed at the same ultimate picture. The ocean had its secrets, and life's whisper might have been growing steadily louder in those hidden, sunless cathedrals of stone. From whichever niche it arose, under the sun's warmth or the ocean's embrace, eventually, the chemistry reached a tipping point. Amid the myriad random molecules, one kind of molecule might have appeared that was different from the rest. Picture a slender strand, like a tiny ribbon floating in the water, made up of smaller pieces linked in a chain. Perhaps it was something akin to RNA, a molecule that today carries information in living cells and can also fold into shapes to perform simple tasks. This long-ago strand, by sheer luck, had a remarkable property. It could make a rough copy of itself using other molecules around it. When it was in just the right environment, maybe clinging to a mineral surface or bobbing in a gentle current, it catalyzed chemical reactions that assembled a complementary partner strand. And from that partner, another copy of the original could form. It's hard to overstate how magical this would be. Up to this point, molecules were created by chance and destroyed by chance. But now, a molecule could template the creation of its likeness. It wasn't perfect. There would have been mistakes in copying, little changes here and there. Yet sometimes, a mistake might make the new strand copy itself a bit faster or survive a bit longer. And so a kind of molecular evolution began. Over time, those strands that were better at self-copying became more common in the chemical crowd. This was not life as we think of it, no cell walls, no true metabolism yet, but it was a crucial spark of life's essence, the ability to reproduce and pass on changes, the beginnings of heredity. Scientists lovingly call this hypothetical chapter in our planet's history the RNA world. In this imagined time, before DNA and before proteins as we know them, RNA-like molecules ruled, simple, floating threads of code and catalyst combined. They might have coexisted with other helpful molecules, perhaps peptides, tiny proteins that stabilized them or aided in primitive reactions. In some versions of the story, life might have started even a bit differently. Maybe simpler metabolic cycles kicked in first, a dance of chemical reactions using the vent's natural gradients, and only later did genetic molecules like RNA take over. We don't know for sure, but eventually both paths converged to the same place. A tiny protocell that could both carry information and perform chemistry, encased in a fragile membrane of its own making. Imagine that moment, if you will, in a microscopic pocket of warm water, perhaps on the clay of a tidal pool or inside a vent's porous rock. A little bubble forms around a set of these molecules. A sphere of fatty acids, like a soap bubble, gathers up just enough of the right chemicals inside it. Fatty acids, simple oily molecules likely present in that early ocean, have a convenient habit. They naturally assemble into hollow spheres in water, as if trying to form tiny cells even without life's guidance. No complex machinery is needed for this to happen. Just the meeting of oil and water can create a delicate membrane. Thus, our little bubble could form all on its own, nature's first attempt at a container for the budding spark of life. Within that vesicle, a strand of the self-copying molecule is sheltered from the outside chaos. The bubble jostles about in the fluid, and inside, the strand makes a copy of itself. And then there are two. Maybe they split up between two smaller bubbles when the original bubble grows and divides, purely by physical forces. Now there are two protocells containing similar strands. It's not yet life in the full glory of a bacterium, but it's a step closer. A simple little system that can grow, replicate, and evolve, drifting in its tiny world. Of course, these earliest cells were incredibly fragile. Many probably fell apart almost as soon as they formed, spilling their molecular cargo back into the soup. But some bubbles might have lasted longer, especially if they were a bit larger or had the right mix of fatty acids. If a bubble managed to grow and then divide into two, each taking some of the replicating molecules inside, then something important had happened. A lineage had begun. Those bubbles that broke apart too easily would leave no copies, but those that could split while keeping their precious contents safe effectively reproduced. Over countless cycles, the more stable protocells and the more efficient replicating strands likely survived better than the rest. In this way, even before true cells existed, a kind of natural selection was at work among these bobbing microspheres of life's earliest ingredients. This might have been how the first true living entities took hold, not with a sudden jump, but gradually, a continuum from complex chemistry to simple biology. Abiogenesis is the word we use for this transition, meaning the origin of life from non-life. It feels almost poetic, the line between chemistry and life blurring until one becomes the other. Over countless cycles and gentle collisions of molecules, the inanimate began to stir with a spark of persistence, a drive to continue, to make more of itself. In the grand scheme of things, it was a humble beginning, quiet and small, but it was profoundly significant. After this point, Earth was no longer a lifeless planet. The seeds of biology had sprouted in its waters. Even now, scientists are not entirely sure which combination of these environments and processes truly gave birth to life. Perhaps it was in the sunlit ponds, or perhaps in the deep ocean vents, or possibly life had multiple false starts in different places before one succeeded. The truth is buried in the mists of deep time, in traces too subtle for us to find easily. Researchers today continue to experiment, recreating early Earth conditions in laboratories, searching for clues in ancient rocks, studying other planets for hints, and testing many hunches. They've found, for example, that certain clays can help small molecules link into longer chains, and that hot springs can create cycles ideal for forming complex chemistry. Each new discovery brings us a little closer to understanding, but the full answer still eludes us. The full picture remains one of science's most captivating mysteries. Perhaps, given the right ingredients and enough time, life emerges naturally, almost inevitably. Or maybe it required a rare stroke of luck. Either way, the fact that it happened here fills us with awe. Our story so far has assumed that life's first spark ignited here on Earth. But what if, in a twist of fate, the spark came from somewhere else entirely? There is a theory, fanciful yet intriguing, called panspermia, literally meaning seeds everywhere. It suggests that life might not have begun on Earth at all, but was seeded here from the cosmos. Imagine a tiny living cell, perhaps a hardy bacterium, hitchhiking through space. How could that happen? Well, consider that in the tumultuous early solar system, enormous asteroid impacts were common. If a large meteor struck a life-bearing world, like a young Mars or another early planet, it could blast bits of rock into space. Encased in some of those rocks, sheltered in microscopic cracks, could be sleeping microbes or spores. In the cold vacuum, most would perish, but the hardiest might survive in a dormant state, like a bear in hibernation or a seed waiting for spring. For years, decades, maybe millennia, the rock carrying its tiny passengers wanders through the darkness between worlds. Now picture one such rock, after a long and lonely journey, being captured by the gravity of a planet, our Earth. It plunges through the atmosphere as a meteor, fiery on the outside, but perhaps still cool deep inside. It lands, maybe with a gentle splash into the ocean, or by coming to rest on soft soil. If that surviving microbe inside wakes up to find itself in a warm, wet environment, it might begin feeding and dividing, oblivious to the fact that it has changed planets. If it thrives, then life has successfully made a cosmic voyage. This scenario might sound like science fiction, yet scientists have found tantalizing clues that keep it alive as a possibility. Meteorites from Mars have been discovered on Earth, solid evidence that pieces of one planet can end up on another. One such Martian rock, found in Antarctica and known as ALH 84001, was even claimed to contain tiny fossil-like structures, hinting that Martian microbes might have once existed, though that remains unconfirmed and debated. Still, just the possibility sends our imaginations soaring. And some bacteria are incredibly tough. Experiments have shown that certain microbes can survive the harsh radiation and vacuum of space for years, especially if they're nestled inside rocks. So it's not impossible that life could spread from planet to planet in this way. Some researchers even suggest that early Mars, which had liquid water and temperate conditions before Earth did, could have been the original cradle of life in our solar system. Mars might have birthed tiny microbes when Earth was still sterilized by impacts, and later sent them here on drifting stones. In that case, all life on Earth, plants, animals, and us, would essentially be Martian immigrants, carrying the legacy of a second world. Of course, panspermia is still a speculative idea. There's no conclusive evidence that it happened to Earth, but it reminds us of something profound. Life might not be an isolated phenomenon. If life could travel between Earth and Mars, perhaps it could travel between star systems over the eons, hopping from one oasis to another. One could imagine microbes frozen in the heart of a comet, slumbering as it sails through the silent, interstellar dark for millennia. the faint light of distant stars its only companion, until one day gravity guides that comet into the pull of a new sun, where it eventually falls into the oceans of a distant planet light years away, seeding a new world with the beginnings of life. Whether or not life on Earth began out there, panspermia expands our sense of wonder. It suggests that in the grand garden of the universe, the seeds of life might not stay put in one soil. They may drift on cosmic winds, waiting to take root wherever they find fertile ground. In our minds, we can hold the beautiful image of life sprinkling through space like dandelion seeds on the breeze, subtle and patient, turning barren worlds green in the fullness of time. However life's origin happened, once that spark did take hold on Earth, it did not remain a mere flicker. Over the eons, that first simple life grew more varied and more complex, gradually transforming the whole planet. For billions of years, the only inhabitants were microscopic, invisible to the naked eye, yet profoundly influential. They blanketed the oceans and crust, feeding on chemicals and later on sunlight. Indeed, at some point, some of those tiny cells learned a revolutionary trick: to capture sunlight and use its energy. Through this innovation, photosynthesis, they began releasing a new gas as waste: oxygen. At first, oxygen was poisonous to many early microbes, but gradually it accumulated in the air and transformed the planet. The hazy, orangish skies of early Earth began to clear and turn blue. The oceans, once filled with dissolved iron that made them look green or brown, turned a clearer blue-green as that iron oxidized, rusted, and settled to the seafloor. The world was changing, driven by the breath of life. It took nearly 3 billion years of Earth's history just to go from that first microbe to the first multicelled organisms. If we imagine Earth's history as a single day, life spends the first 20 hours or so in that microscopic stage. The emergence of larger, complex life doesn't happen until late in the evening of that day, and everything humans have ever done would fit into the last few seconds before midnight. Life, it seems, was unhurried in its development. Yet with oxygen came new possibilities. Life could access more energy than ever before, enabling new forms to evolve. Single cells started cooperating, merging, and specializing. By around 2 billion years ago, some cells had combined forces to become larger, more complex cells with specialized parts, the ancestors of all plants and animals. Still, time moved unhurriedly. For the majority of Earth's history, life remained at the microscopic stage, quietly preparing for what was to come. Imagine the oceans around 600 million years ago, soft-bodied creatures drifting in ancient seas, like strange jellyfish and frond-like animals waving on the ocean floor. Then came the Cambrian explosion, an evolutionary flowering when countless new forms appeared: shells, eyes, claws, fins, a true flourish of creativity by nature. As if evolution were playfully experimenting with every shape and strategy it could. Life was no longer just tiny specks in water. It had grown into an array of beings of all sizes. Not long after, in geologic terms, green algae and simple plants began to colonize the land, followed by the first brave animals crawling out of the water to explore the barren shores. Ferns and primitive forests spread over the continents, and insects soon buzzed through ancient skies. Fish, with strong fins, hauled themselves onto muddy banks and became the first amphibians. The adventure of life had breached a new frontier. The solid ground that had once been nothing but empty rock now teemed with green plants and crawling creatures. Through cycles of change, through extinctions and new beginnings, life's narrative continued to unfold. For a long age, dinosaurs of all shapes and sizes roamed across warm, fern-filled landscapes. In those days, huge forests and swampy jungles rang with the calls of creatures unlike anything seen today. But eventually, their time passed. In the quieter world that followed, small mammals that had lived in the dinosaurs' shadow emerged, scurrying and flourishing. These mammals diversified into a myriad of forms. Among them were early primates who swung in the trees. And much later on, a branch of those primates climbed down, stood upright, and began to gaze at the stars in wonder. We reach the recent chapters of Earth's story, the age of humans. Now, in the present day, we humans have the privilege of reflecting on this grand history. We even find tangible echoes of those earliest times. We dig up ancient rocks to find the faint traces of those first microbes. For example, fossilized microbial mounds called stromatolites, some nearly 3.5 billion years old. And we marvel at how a planet could go from lifeless to vibrant. We discover fossils of creatures from all stages of this journey and piece together the chapters of our deep past. In doing so, we connect with every organism that ever lived. The grass, the birds, the whales in the ocean, and us, listening here now, are all relatives if you go back far enough. Life's family tree has one root in that primordial time. How incredible is it that a simple cell, born in a hot spring or a deep-sea vent, through an unbroken chain, led to everything we see today. This knowledge can give a sense of comfort and belonging. We are products of Earth's long striving, part of an unyielding lineage that weathered cataclysms and ages of ice and fire. Our story is truly Earth's story, and if life could flourish so abundantly here given enough time, it stirs the question, could the same not happen elsewhere? As we contemplate our own origins, it's natural to wonder, could the story of life be playing out elsewhere in the universe, too? The Earth may not be the only stage for chemistry to become biology. In the vastness of space, scattered among the billions of stars, there are countless planets and moons. Some of them are surely kindred to our young Earth, with warm oceans, volcanic energy, and rich chemistry waiting for a spark. Even in our own solar system, there are tantalizing prospects. On Jupiter's moon Europa, for instance, a global ocean lies hidden beneath an icy crust. In that dark ocean, warmed from below by hydrothermal vents on the seafloor, could there be simple life forms drawing energy from the heat, just as microbes do around Earth's vents? Over on Saturn's moon Enceladus, geysers of water shoot into space from another subsurface ocean, hinting at an environment that might be friendly to life. And Titan, Saturn's giant moon, has lakes of liquid methane and ethane. It's a frigid, alien chemistry vastly different from our water-based life. But one can dream. Might some form of life find a way to make a home in those hydrocarbon lakes, with slow metabolisms suited to the cold? Beyond our solar neighborhood, the possibilities expand exponentially. Astronomers have discovered thousands of exoplanets orbiting distant stars, and many more surely await discovery. Among them are planets that appear to have the right conditions, neither too hot nor too cold, possibly with liquid water and protective atmospheres. It's easy to imagine that on one of those far-off worlds, under the glow of an alien sun, there are rivers and seas where chemistry is experimenting much as it once did here. Maybe on a planet circling a gentle red dwarf star, the sky is a different color, the air thicker or thinner. But in a warm pond akin to our primordial soup, organic molecules are forming and joining. Perhaps small RNA-like strands are already replicating in those alien waters, unaware that on a planet across the galaxy, creatures called humans are pondering their existence. We also know that the universe has been generous with the ingredients of life. Organic molecules, even sugars and amino acids, have been detected in the dust clouds between stars and on meteorites and comets. The cosmos provides a starter kit almost everywhere. Given time and the right conditions, who knows how often that kit assembles into something alive? Life might be less of a rare miracle and more of a common refrain, humming wherever conditions are calm and favorable enough. Of course, until we discover evidence of life beyond Earth, these scenarios remain lovely possibilities dancing in our imagination. Perhaps one day, scientists will tune a sensitive telescope and detect the faint chemical signature of life in the atmosphere of a distant exoplanet. Or maybe a robot submarine will swim beneath Europa's ice and catch a glimpse of something wiggling in the dark water. But even now, simply knowing that it could happen is comforting. It means that the story we've told tonight of life emerging from inanimate matter might not be unique to our world. It could be a universal story told in a million variations on countless planets. Just picture it, far across the galaxy, on a quiet world orbiting an ancient star, gentle rains fall on a young sea. Perhaps twin moons hang low on the horizon, casting a faint silver light on alien tides. Unknown constellations shimmer in its night sky, patterns of stars that our eyes have never seen. In that sea, perhaps alien molecules are linking up, forming their first tentative systems that could spark into life. Their path might be different from ours, their biochemistry could be exotic, but the essence would be the same, the quickening of something that can grow and evolve. In the grand theater of the cosmos, life might be opening its eyes for the first time in many places, reaching out, however blindly, for the light. Such thoughts can fill one with an immense sense of connection and wonder. Whether we are alone or one of many, the fact that life happened here at all, and possibly elsewhere, is a gift of cosmic proportions. We are a part of this universe that has become alive and aware. And if there are others out there, then in some intangible way, we are not just in our quiet room on Earth tonight. We are part of a greater community of living things sprinkled throughout the stars, all sharing in the miracle of existence. Tonight we've journeyed through time and possibility, from the fiery birth of our planet to the gentle spark of the first living cell, and onward to the idea of life spreading among the stars. We wandered through warm primordial pools and deep-sea vents, through meteor showers and distant planets in our imaginations. All these paths, all these theories, paint a picture of a universe eager to give rise to life, in one way or another. The origin of life is a story with many chapters still unknown. Yet thinking about it can be oddly comforting. It reminds us that we are connected to the Earth and the cosmos in the most intimate way. The very fact that you are here, breathing and listening, means that an unbroken chain stretches back from you to that first cell in the primordial sea. Every bird, every tree, every person is a part of that chain. We are all children of that ancient dawn, carrying a spark passed down across billions of years. The salt in our blood and the water in our cells echo the ancient ocean where life began. The iron in our veins was forged in distant stars long before Earth existed. In this way, we carry pieces of Earth and cosmos within our very bodies. We are, each of us, little pieces of Earth's life, come awake to wonder at our own beginnings. Now, as your eyes grow heavy and the thoughts of the day fade away, you can feel the gentle pride and peace of being part of this grand tale. In a way, the universe has been unfolding for billions of years, just so that you could be here in this moment, alive and aware. And as you drift into sleep, you carry within you that deep history, that connection to the first life and to the stars above. If you enjoyed exploring this mystery with me tonight, you might consider leaving a like or subscribing for more gentle journeys like this one. I'm truly grateful you chose to spend these moments in curiosity and calm. But for now, there's nothing more you need to do. You can let go of the questions and let your mind rest. The science and the wonder will be here waiting for you whenever you want to wander again. The night is deep and kind outside. The same earth that nurtured life's dawn is turning calmly under the blanket of the sky. The waves will continue to lap at the shores. The stars will continue to shimmer overhead. And life will quietly go on evolving and thriving, all while you simply breathe and rest. As you drift towards sleep, allow the images of our journey to gently float through your mind and then dissolve. Picture the fiery glow of the young earth gradually giving way to cooling rains and steaming oceans. See the silent, starlit nights of long ago, when meteors danced across the sky and warm tides ebbed and flowed under an alien moon. Imagine the quiet rock pools at dawn, with faint wisps of mist and the first spark of life trembling in the water. Envision the deep ocean vents, glowing softly in the darkness, cradling the earliest chemistry in their warm embrace. And above, the endless cosmos, with comets and dust carrying seeds of possibility from star to star. All these scenes are like gentle waves in your memory now. You can watch them ripple and then fade, leaving behind only calm. So let yourself sink into the mattress a little more. Feel the weight of your body ease into comfort, and know that you are safe and you are home on this precious living world, cradled by the vast universe around us. Let the enormity of time and space reassure you that all is well. Creation goes on, and you are part of it always. You are cradled by the earth tonight, just as tenderly as that first tiny cell was cradled in the ancient sea. In this quiet moment, you are connected to that gentle beginning and to all life that has ever blossomed from it. Good night, fellow traveler. Sleep well, your home among the stars.